Hello, everyone. I'm Chris Galley, postdoctoral researcher with the Metal Oceans Group under Mark Hannington, and here to give an update on the gravity modeling I've been doing in the Superior Province. Here just to recognize our government funding academic partners and the software that's involved in the research. And then as far as the objectives for this talk, it's give an update on the work I've been doing thus far, pretty well aimed at identifying rifting features in the Abitibi and then the Superior Province in general. Idea being behind VMS are largely produced in rifting environments. So we are aiming to figure out some way of determining where these rifts might have occurred in the Archean in the Abitibi to potentially explain the distribution of VMS there. And then use the method elsewhere in the Superior to potentially explain why there would be less VMS, for example, in the Western Superior. And we accomplished this through the 3D inversion modeling of gravity data. The two models that were produced, the one here is the Abitibi model, and then that is compared to the Western Superior model, this black outline here, to pretty well compare and contrast a well-endowed area in the Abitibi to a less well-endowed area, Superior, from the point of view of VMS endowment. The two gravity data sets that are used for the modeling, one for the Abitibi was from the GSE. That was uh, uneven distribution. It's compilation data sets. So at a minimum, it was thin. So there was 5 kilometers between data points, but in some cases there was 10. Overall, a little under 4,000 data points. For the Western Superior model, because it crossed international boundaries as well as going over water bodies, I used a global data set compilation. This one developed here and credited to 10 kilometer spacing, just to get more even model continuity over these boundaries. Uh, Pretty well how our models are produced is through inversion modeling. So what you do in inversion modeling is you take your gravity data as your input. This is the gravity data from the Abitibi. And then you break up what you want to model. So in this case, section the Abitibi into pixels that you can solve for the density in each of those pixels. We use tetrahedral pixels because we're able to fit the uneven topography in the area, as well as have efficient padding regions around our area of interest where we can have smaller cells and higher resolution. Um, and then you take these two inputs, the structure of your pixels, the gravity data you want to model, and the inversion model will iteratively solve what density is required in each of these pixels, such that if you measured the data your model produced and compared it to the data that was collected, the real data, they should closely match, ideally near zero, and then the inversion model will continue iterating until that closeness has been reached. And what that'll then give you is sort of shown on the right here, um, is a semi-continuous distribution of density throughout your model region. And this is just then cut open that from our 3D density model, there's a number of things you can look at studying, but what the aspect of it that we're focusing in on is the Moho. The Moho is typically derived from seismic models, so sort of a velocity feature. But you can also derive a proxy for the Moho from density distributions. And previous studies have shown that by looking at the 3.07 grams per cubic centimeter uh, density isolayer, this can well represent the Moho. This is a little bit of background. This sort of Moho modeling certainly isn't new, but the resolution is sort of where we're pushing things. So here are some examples, such as Australia, Africa, South America, where some large regional Moho models have been produced and have been successful, sort of compared um, to seismic models. But largely to make things a bit more computationally efficient, some assumptions are typically made. Main assumption being in a lot of these models is you have uh, horizontal homogeneity through your layers. So this is just a little diagram of this showing that the upper crust is sort of held at one constant density. Same for the lower crust, same for the mantle. So the density in the mantle, or sorry, the density in these models don't change, but rather the height of the interfaces between them are able to be changed. And that's how these Moho models are produced. And a similar method has actually been used previously in the Western Superior in a small area here, over English River. Um, but where we sort of push things is rather than assuming homogeneity through sort of the upper crust or lower crust through these crustal layers, having the pixels be broken up and have them vary in 3 dimensions, let the density vary in 3 dimensions. So you're able to more accurately reproduce what we see in the crust, such as you have in the upper crust, low density plutons beside high density greenstone belts. So right away, this sort of assumption has some limitations. Computationally efficient, good for really large models, but we wanted to make something a little bit more accurate, which led then to our 3D model that we could extract this proxy for the Moho out of. Um, to sort of start things off with the Metal Oceans program and having that modern perspective into our modeling, we didn't want to jump immediately into the Archean. We wanted to start with this modeling methodology in a region where we can be sure that the rifts our model resolves actually coincide with real rifts. So the modern seafloor is perfect for this. Is in the bathymetry sea rifts. We know where they are. We don't necessarily need to look at the Moho topography, but there are still very interesting things sort of extracted from that, which we won't get into. But the main aspects is here on the left. You have the bathymetric surface of the Lao Basin, which is actively opening back arc basin in the Southwest Pacific, so east of Australia, north of New Zealand, and it's filled with hydrothermal vents, sort of the modern equivalents to the ancient VMS. And you can see that they largely produce where you have heat. So in these area of rifts, so these black lines are little arrows to denote the spreading centers, sort of where you have accretion or sorry, sort of crust being produced um, in the back arc here. Looking at the Moho model, our 3D produced a 3D density model, extracted the Moho from that. You can see, as you might expect, that along the spreading centers where you have this focused extension, you have a thinning of the crust because the mantle, the crust will be stretched, it'll be thinned, the mantle will be pulled up, as well as, in the bathymetry, the seafloor will deepen, sort of a thinning on both ends. So we're able to see present extension as local thinning features, ancient extension that would have occurred in the forearc as the back arc basin first initiated, but also ancient extension sort of on the west side here. So when the back arc first started opening, it was largely rifting that occurred, and then spreading centers tend to jump towards subductions. Then it jumped over, and you have now the spreading in the east. You can see that the model is able to resolve these rifting features. Now we looked at the Lao Basin. It happens to have a subduction zone. Certainly not inferring that there's any sort of subduction that would have happened in the Abitibi, but more this model was really able to show that we are able to model extensional features that present as crustal thinning by studying the Moho topography. So then we did the same thing in the Abitibi. So this is now the Moho depth. Not calling it crustal thickness. That can kind of infer that we know what the crustal thickness was during the Archean, which we do not. There are some estimates on what erosions take place since, but don't really want to get into that. So just going to refer to as present Moho depth. But the premise is the same. Where you would have had extension, the crust would have thinned. You would have the mantle infill above. Upper crust likely would have thinned also. But since then, there's been erosion, you've had compression, there's been a bunch of imbrication that's occurred in the upper crust. Due to the thickness of the Archean crust, the Moho is well below the brittle ductile boundary. And from seismic profiles, it is shown that all the imbrication and thrusting has occurred in the upper crust, and this did not reach down into the lower crust in the Abitibi. based on the seismic profiles we've seen. Thus, then, when you would have compressed the Abitibi, even though you would have gotten thrusting and faulting in the upper crust, that would have rotated and messed up some of the features and certainly made it very difficult to identify any sort of rifting features at surface. The compression uh, would have, well, compressed these drifting features, but the shallowing of the moho would still be present even when compressed. It would be exaggerated a little bit, but it would not get overwritten through the compression. At least we don't believe so. And the model here then shows sort of in blue where you have shallower moho um, lines up really well with BMS. So we sort of believe that these shallowing of the moho would correspond to rifting features, but of course we wanted to compare this to other independent um, factors such as VMS distributions. So we see VMS largely where you would have had shallowing of the moho. Not all VMS in sort of this deeper moho, thick and crust areas. There are some, although they tend to be smaller in size, much like on the modern seafloor. Anywhere you have heat sources near surface, you can generate hydrothermal circulation, where it's really at these rifts where you have sustained heat source from the shallowing of the moho that you can produce larger VMS. Here's a cross section through Noranda and Matagami, shown on the bottom here of the three density models. You can see at the lower density plutons at surface. Density of the crust increases at depth up until well, beyond the moho, but we sort of cut it off there just to visualize. And the below here is a 5-to-1 vertical exaggeration of the moho, just to show how you have shallowing under Noranda as well as Matagami, where you have these large camps of BMS. And the crustal scale faults that we're seeing here sort of believe are Hofgraben features that might have formed during the initial extension of these drift features. Um, so then adding on some interpretation to our model, if you look at all these rifts lining up, they do tend to form these sort of islands of deeper moho or thickened crust that we believe might have been some sort of microplate mosaic. Um, Certainly not all of these spreading centers or potential rifts, spreading center probably isn't the right word, were active at once. Here's an age map of the Abitibi, sort of the purples being older rock, blending into the yellows down the south, being younger crust. So you can see that in the north is where you have there's a little bit of older crust in the south as well as the north. So it appears that if these were in fact rifting initiated in the north, you have crustal production. There's then this corridor, there's a oblique corridor of shallowing of the Moho that extends down to meet up with these interpreted southern rifts. And this lines up with a branch of the Kid Monroe. So we're interpreting this as a series of on echelon rifts that would have jumped down uh, through the Abitibi until rifting then established along sort of Blake River, Pathmasson, Timmins, into Val-d'Or, down in Swayze, down in the southern area. Because we don't see sort of the same kind of bounding fault features we do see in the rest, but we do see still those east-west faults down. A feature we actually see also in Iceland, where you have on echelon rifting connecting a dying spreading center over to the eastern more active spreading center. And then to sort of add on a bit more independent um, data sets to help bolster our claims that these could have been rifts. We have some isotope data taken from one of Mo's studies. So here's the epsilon hafnium data indicating depleted mantle, where it seems like we have mostly depleted mantle over these interpreted rifts. The VMS here also in red, just showing again they line up well with interpreted rifts. And then looking at the strontium over atrium, indicating shallow melts. Again, sort of the shallow melts indicate where or line up well with the rifts. In David Mole's study, he also kind of interpreted these to likely be where the rifts would be. Um, and then sort of the other data sets here that can indicate then thickness of crust. So through distributions of EMS as well as geochemical data, and then our geophysical models, they all tend to be pointing towards sort of these rift-like features that likely exist in the Abitibi. Uh, that then takes us to the second model I'll talk about, which is the Western Superior model. Here's the Bugey data that we inverted, and then this is the Moho map that was produced, same way that the Abitibi Moho map was produced. Um, Much like with the Abitibi and even the Lao Basin, we always want to constrain the models to the seismic, any kind of seismic profiles that are through. So here's one example of the lithoprobe seismic section that ran the length of their down sort of a north-south component of the Western Superior here. Um, Here's the section. The have a dotted line is the refraction model. The color is the interpreted reflection model, and then the sort of white black line is our Moho derived from the gravity model. You don't quite see it well with the one-to-one vertical exaggeration, but here at the 5 times vertical exaggeration, it shows things a little bit better where, in color, there's the interpreted reflection, but the refraction, which is more accurate, less assumptions are made in the velocity model of the crust, lines up well with our gravity model. So this line being the Moho for the gravity model, this sort of white transparent window is the uncertainty of the model. So the refraction fits well within that. Uh, but a bit more importantly, not only do the depths line up well, but the shape, which if we're interpreting thinning and thickening of the crust or shallowing and deepening of the moho, those are sort of the features that we care most about. So it's good to see then where in the reflection you had shallowing of the moho, deepening of the moho. You can see that is reflected also in the gravity modeling. Um, Now, just to sort of take out the digital marker and add on some interpretation, we started trying to make sense of what's going on in the Western Superior, because it's quite a bit more complicated than what's happening in the Abitibi. So here's a geologic map on the left. Here's the Moho model on the right. Um, Starting up in the north and sort of traveling south. Now, this wasn't really the focus of the model, but an interesting feature nonetheless I'll point out is that the arc, which would have been thick and crust at the time, so what we'd expect to be a shallow moho now from the Flin Flon arc is a sort of a deepening moho. You have the Kissimmee domain, which was interpreted to be a back arc sort of basin, thinning of the moho as you expect, and then the Larange Lynn Lake arc also. So good to see that there. Then into the Pickwetney domain and the thickening of the boundary there of the Superior province, and then get down into sort of these concentric uh, deep moho bands radiating from the Bering River's Pluton complex, sort of at the heart of the North Caribou. And we believe this could be explained from the tectonic models been presented. This is shown from one of Percival's work. A few people have shown this as well, where the North Caribou sort of acted as a bit of a nucleus that then other terrains layered into. So we believe that these bands of deepened moho likely correspond to bands of accretion, where the centers would have slanted into each other. You would have had local thickening of the crust, which you now present as deepening of the moho. So you're able to see those extend, as well as you can see then these Archean features extend below sort of the cover to the west and extend. So we're able to see these things um, below thick cover. Uh, Traveling a bit more south, we have the English River Suture shown to be um, thinning, and then this interesting fe feature here, sort of this deep moho little band sticking up, which has been interpreted to be an accreted oceanic plate. So again, calling on the interpreted seismic lithoprobe profile. This dark green is interpreted to be oceanic crust, Archean oceanic crust that might have um, accreted below sort of the Winnipeg River and Marmion and Wabigoon. Um, and in our model here, it showed as, or in the seismic, it showed as a deepening of Moho, and we can sort of see this then in 3D, the shape of this potential accreted plate with a hole punched into it where the Nipigon intrusions as part of the mid-continent rift would have then ripped a hole in it a little bit, which then, last but not least, the very prominent mid-continent rift presented as you'd expect to be a shallowing of the Moho, as this large rifting feature. Um, Now that we're starting to get a few models together, we're still hoping to continue making more and more data points will just make the interpretation hopefully a lot more clear and simpler. But at least with these three models, the Lao Basin that we have on the left here, the Abitibi model that we have in the center, and then the Western Superior that we have on the right, we're hoping to be able to explain why there might have been more VMS in the Abitibi, and then there appears to be less in the Western Superior. And sort of as mentioned, the argument is the amount of rifting and the prominence of rifting. Um, Sort of as an attempt to come up with some way of quantifying rifting, we looked at the histograms that the Moho depths of the Moho depths from the different models. So starting with the Abitibi here, this is the color bar for the Moho depth, and then the histogram produced, you know, especially compared to the Archean crust, thinner, about on average almost 14 kilometers, with a standard deviation. It's not quite Gaussian, roughly, but a standard deviation about 2 kilometers. We're then looking at the Abitibi model and the Mid-Continent Rift model. The Mid-Continent Rift is part of the Western Superior model. I just kind of took that puzzle piece out and now treating it as a separate piece for sake of interpretation. But looking at the region that encompasses the Mid-Continent Rift, so this is sort of the yellow here. You see actually a very similar amount of variance, the similar size standard deviation to the Moho depth within the Lao Basin. And then looking into the Abitibi, where we propose there was rifting along these sort of these shallowing the Moho centers. This is on the blue histogram. Again, about 2 kilometers in standard deviation, very similar variance. But then comparing to the Western Superior, then just trimming to the Archean portion, you have a much more narrow band. So on average, the crust appears to be a bit thicker, but you just also don't see the variance in crustal thickness, or in Moho depth, I should say, as we did in the Abitibi or in the Mid-Continent Rift or in the modern uh, Lao Basin. And you can see this. You don't have, the prominent blues. You don't have the prominent shallowing of the Moho alongside the deepening of the Moho, or the same kind of interconnected bands, sort of potentially interconnected rift features that, we see where we know the rifts, Mid-Continent Rift, Lao Basin, where pros there are. You don't see them here. You do still see some shallowing. There was probably some heat sources coming near surface. You do have VMS, so there was near surface heat driving hydrothermal circulation, but we don't believe there is as much VMS occurring in this area, likely because the crust is a little bit thicker and it just doesn't appear to have formed the same sort of rifting that there appears to be, or we are presenting there is in the Abitibi. So in conclusion, we produced 3D density models, three 3D density models, one for the Lao Basin, one for the Abitibi, one for the Western Superior, um, and are using this to figure out how to identify rifting features in the Moho, develop the modeling methodology, show what they look like, and then apply it to these Archean terrains for both a well-endowed uh, area, the Abitibi, and then comparing to less well-endowed. So here's just a snippet of the West Wabigoon. Really, the takeaway that we seem to be seeing is in the Abitibi, you have what appear to be very prominent rifting features. These are backed up with the distribution of EMS, which lie largely on it, as well as a number of different geochemical data sets also closely correspond to that. Then looking at the Western Superior, such as the Western Wild Lagoon, you don't really see the same sort of rifting features. So we just don't think you really developed the same level of rifting, which would then produce the same amount of EMS that we're likely seeing in the Abitibi. Uh, thank you. Thank you for listening.